That's good. Okay, well, that's all I wanted to check. All right, everybody's settled in. I think there's no reason to not begin our presentation. I appreciate having a full room. Late arrivals. We're going to have to bring out chairs to the outer edge, I think. So thank you very much. So again, I'm Matt Weldon, and I'm the industrial program coordinator here. So along with Larry and I, we work with some of our external industrial membership within Nascent. And I'm very pleased today that we've been able to bring Dr. Zheng to present his group's research to us from main campus. And so for those in the Nascent community who might not have actually taken time to read the presentation flyer, he got his doctorate from Pennsylvania State and then did some work at Caltech before joining us here at UT. And I'll let you present other details. Thank you very much for coming. And let me make sure that PowerPoint is ready to run. And there you go.
Okay, thank you. Can you hear me at the back? But the speak only for the waiver purpose. So basically you hear my original voice. And so first, I started with an overview for our research. So we explored the light and matter interaction at the nanoscale in the complex fluid environment to develop optical tools, materials, and devices for different applications. So today I'm going to share with you some of our recent results on using light for digital manipulation of digital manufacturing of nanomaterials with complex architectures. So the work is a collaboration between my group, and we have a lot of great groups on campus, also outside of UT. And the work we have done is supported by different agencies. So one of our goals is to use colloidal particles as artificial atoms to create artificial matter or create functional devices. So compared with atoms, like the chemists can create different type of nanoparticles with different materials, different size, shape, which show different property, which very different from atoms. Right? But the advantage for colloidal particles is that you can control the property through shape, size, and composition control, which cannot be achieved when you look at the single atoms. All right, so just give you one example. Usually, metal, we know, can be fabricated into metal colloidal particles, nanoparticles, right? And we may not think too much about the metal for optical applications, maybe unless in the long time ago people using metal as a coating for mirror. But in a lot of cases, we are not using metal for optical application. But interesting optical happen when you have these small metal nanoparticles. Right? Optically, they become very interesting. For example, you have this piece of gold nanoparticle. And it can support interesting phenomena we call surface plasma resonances, which is light coupled to the oscillation of free electron confined by metal nanoparticles. So when you have this resonance, what's happening? So the metal nanoparticle can scatter light or absorb light at a specific wavelength very strongly. Right? So if the light have red color, blue colors, of those particles can show different colors. Right? But it's not just visually looks good. And if you look at the near field distribution, this is 10 nanometer metal nanoparticle, right? So look at those light. It's be confined very strongly toward these small nanoparticles. If you imagine, here is a lens, right? And basically we know the conventional lens, we have limitation in terms of the capability to focus light, right? We have called diffraction limit. So the smallest size you can focus light into usually is half of the wavelength. But look at here, because of these nanoparticles supported surface plasma, they can confine light even below 100 nanometer, reach to the size of the nanoparticles, 10 nanometer here. But if you look at the near field distribution, here's a triangular golden nanoprism. You have very, very highly concentrated light at this tip position. So at a very small size. You can imagine now you have really, really high concentrated light at the nanoscale, and those light can also convert into heating, right? Because of the loss of the light. So you can see you have very, very strong confined thermal heating at the same time. So what we can use for those kind of intrinsic phenomena, and one approach is that we can just like matter, right, using atom as a building block. So can we using these very interesting colloidal particles as a building block to create artificial matters, right, as artificial atoms? But that can be very difficult because in the conventional matter, we know usually atom can self-assembly into different crystal structures. The crystal structure, FCC, BCC, different bonding, ionic bonding, metallic bonding, will determine the property of the matters, right? But how can we arrange those colloidal particles into specific crystal structure, or to introduce interaction or the bonding between them will become very challenging compared with atoms, right? But one very basic approach you may think about is just like you play Legos, right? Can we bring those colloidal particles just like we pick up the Lego piece and put them together in a very precise fashion and in very pre-ordered array, right? But the challenge is it's not like a Lego we can use in hand to pick up, right? It's too small for us to use in hand to pick up one single nanoparticles. So what we can do, one approach people have been exploring is optical tweezers. So basically using light can capture individual nanoparticles, which just won Nobel Prize this week. And the advantage for this type of optical tweezer is that they can provide precise control of the position of nanoparticles. Also, because of advance in the digital micromirror device or other light modulator, we're able to really easily to control the light beam in the arbitrary fashion. So you can imagine now you have this kind of tweezer, can hold the particles, can move them around, and can arrange the particle into different crystal structures. But the limitation for conventional optical tweezer is that usually we need a high power because to using optic gradient force to generate enough force to travel particle, we need high power. And also, since the principle based on optic gradient force, usually we need a high contrast between optical property of the particle and the solvent, so which limit us a lot of different combination of solvent and particle systems. And also because of the high power, so you can imagine this high power will kind of damage the particles you are going to assembly, manipulate. And also we need very complex optic systems because the high quality power can be only achieved using a high numerical aperture length, using a very complicated optic system to achieve very high quality power laser beams. So all these limits application in particular in nano manufacturing because in the manufacturing we hope that the process can be high throughput, can be manipulate a lot of particles, assemble a lot of particles in a very short time. So this high power standard, this complex optic system make this become challenging. So now we ask ourselves, how can we overcome some of these advantages and still take advantage of the versatility of optical manipulation so we can bring this concept into a nano manufacturing domain. So that's exactly what we have pushed into. So exactly what Zheng has been working on is that, so instead of using optical force, which obviously need a high power, but can we still using optical way, but in a very different working principles. One of the working principles is that we using light to generate temperature gradient, right? So using a different kind of mechanism. But a lot of the cases, you know, when the laser hitting substrate, for example, usually you heat it up, right? So you have temperature gradient. You have a hot region at the laser beam, and when you go away from the laser beam, you have a colder region. Right? So a lot of colloidal particles in the suspended solvents, they will move along this temperature gradient. But unfortunately, a lot of time, the motion will move from hotter to colder region. So that means whenever there's a laser beam, basically you push away the particle, so which is contradicted with what our purpose is trying to use in laser beam to capture the particles. Right? So we have to solve this problem. And the Zheng found out that at a certain condition, basically the particle can be moved from colder to hotter region. So one situation is when the particle have very well-defined electric double layer, as shown here. So this is electric double layer from the molecule of the solvent, for example, the water. Now, when they form this electric double layer, what's happening is that actually it flip the sign of this coefficient. This coefficient basically tells us, the sign tells us the direction. If it's a positive or negative, it will tell us whether from hotter to cold or cold to hotter region. And amplitude will tell us how quick the motion can be, right? So as you see, this depends on a lot of different parameters. That depends on solvent, depends on the particle. But look at this term, which tells us it depends on the gradient of the dielectric function of the solvent surrounding the particles and the temperature gradient. So you can see if you have a bulk water, you have this term, it have 1 point negative value. But you have electric double layer, it become positive. So what's happening here? Basically, because of the electric double layer, you flip this sign from negative to positive, right? Or positive to negative depends what the other parameters. So basically, you are able to control the light now, or control the particle now, start moving from colder to hotter region. So that's exactly what we achieved in these demonstrations. We have these laser points. They have the heating hot source, and it turns out that those particles will move toward those laser beam position. And it can naturally apply to biological cells because biological cells usually have a charge, right? So very naturally for them to form electric double layer surrounding these biological cells. So we can use this laser beam through the temperature gradient to achieve the manipulation. I compare with conventional optical tweezer, and we achieve this manipulation using the laser power, which is 1,000 times lower. And we don't need a very complex systems. And I keep challenging my students, say, can we use the laser point to achieve this kind of manipulations? So you can imagine we can dramatically reduce the complexity of these systems, right, to achieve a highly portable device, which otherwise will occupy the whole optical tables, half of the room of these seminar rooms, half space. So, but again, this type of mechanism have limitation because we have to rely on the electric double layer, right, which not always occur in a lot of systems. Right? So we push further. Can we keep pushing the same kind of idea to apply for many different systems, not only the system which have electric double layer? So that's come to another invention that they have with our lab mates have been developed. So we call optothermal electric nano tweezers. So in this case, still using the same thermophoresis phenomenon, but here we add more ingredients into the solvent system. So now here, instead of only the particle we are interested in, we start adding surfactant molecules, CTSE here. And the surfactant molecule have positive charge, and they can form a monolayer surrounding these particles. So the particle we are interested in become positive charge. Also, when you have enough concentration of surfactant molecule, they can form micelle, right? So surfactant have charge, so the micelle is a much smaller size. They also have positive charge. Also, in the surfactant solutions, we have neutrons. So since we need neutrons, which means you have negative ion to count the positive charge of the molecules. Right now, you imagine you have three systems, or three particles in the system. You have colloidal particle we are interested to trap. You have a micelle particle, and you have this ion. Right? So now the same thing when we heat the substrate with the laser beam, you have this temperature gradient. Right? So what's happening for all the particles? They will do thermophoresis. Everyone will start moving from hotter to colder region. Here is a conventional case. But interestingly, some move faster, some move slower. Right? And it turns out the micelle move is the fastest, and the ion is the slowest. So now you have basically, when time goes on, you have separation of a positive ion and a negative, positive micelle and negative ion at this space. So now you have this positive, negative charge, you form electric field. And also the particle we are interested in have a charge. So you can imagine now you have electric force, electrostatic force applied to this particle to confine particle at this laser location. So that's how we achieve using thermophoresis to achieve the trapping of the nanoparticles. So this video shows you that it's a single colloidal silver nanoparticle. And what you see before I turn on the laser is a blue light dot keep moving because of Brownian motion. Right? 100 nanometer, you can imagine it's a keep moving. The reason you can see this 100 nanometer particle is because it has surface plasma. As I mentioned, the surface plasma can scatter light strongly. Right? For silver at 100 nanometer, usually it's a blue light, so you can see as a blue color. Right? So you see when we turn on the laser, oh yes, thank you. Now it's random motion. So when we turn on the laser, now it's become static, right? So how we know is trapped. So we can move the laser beam or move the substrate. So you can see relatively the particle is moved towards relative to the substrate. And when we turn off the laser again, you will see the particles that bright spot will go random motion again. So which shows that now we are able to capture the particle and holding them at suspended in the solution. But how do we know that the particle, the bright spots, what you see is exactly the particle we're interested in, right? So we integrate the tutor system with our spectrograph, so we can measure the spectroscopy. And again, as I mentioned, because of the cytoplasm of these metal nanoparticles, they have a certain resonance they show in the spectrum. So different particle depends on the size, shape, composition. They will show different resonance. So we can combine the experimental measurements with the simulation, so we can figure out what type of particles we are trapping. So you can see this technique is generally applied to many different particles, different shape, different size, and different later on we also different compositions. And of course, we know that because the progress in the digital micromirror device, right, just like the chip in this project, where very conveniently we can control laser beam from one single laser beam into a lot of laser beams, right? So we can do parallel trappings. So here you can see one single laser beam we can split into 6 beams, right? Each can capture one particle, and we can do parallel manipulations. More interestingly, when we bring 2 particles together, and now just in analog to the matter, right? We mentioned for atom that you form bonding, you form matters. So how you form bonding between artificial atoms, those colloidal particles, and we introduce one type of attractive force between 2 particles. When the particle how I come up with the laser point, that laser point?
Yeah, you just ask for
Oh, okay. All right, thanks. So when we bring 2 particles close enough, when the distance it becomes too small, that they cannot hold this missile particle anymore. So this introduces the unbalanced concentration between the missile surrounding the particle and the between particles. So now because of much more missile surrounding this particle pair, we introduce force between these particles. You push these particles together, right? And what we call this called the depletion attractive force. So this can be imagined as artificial bonding. We introduced between these artificial systems. So because optically, when you bring these 2 particles together, you will see very interesting optical signature change, right? From 1 peak to 2 peak because of the coupling happen. So now we can enable more precisely control the distance between the particle by simply control the concentration of the micelles. So now basically we'll create here is a dimer, right? Or we can create a lot of atoms, create artificial matter which have a tunable bond length. Right? But conventionally the matter, we know for any type of bonding they have specific lengths. Right? They have specific bonding energy, which means the matter usually not easily tuned. But here, this artificial matter, we are enabled to real-time tuning their bonding length, tuning their interaction to achieve tunable properties. So now we have the capability to capture the particle, arrange them, introduce bonding between them. So now exactly what do we need to do for Lego, right? And we bring the Lego pieces together and click them through a mechanical click. But here, because we introduced the artificial depletion attraction, now we can do similar thing, just like play Lego. So this video shows that we can do this in a polar situation. Given the particle and in the given size can be manipulated at the same time. But we can also do one by one. But you see, if without the interaction, you can imagine whenever you push the particle there, they'll always be disassembled again, right? Here, basically, you're just like a click your Lego piece because of this attractive force. So once you get this piece, we can rotate it, which means it's very robust. And the bonding between the particles is strong enough to hold this as a whole piece. And we can even, because of a lot of time is anisotropic particle, right? So how can you control the orientation? So we create a one-dimensional laser beam, which enable us not only capture the particle, also control the orientations. So we can do more complicated assembly of those colloidal particles. So we can do many different type of particles, different composition, different size, and create them into many different configuration. Right? If it's a small several particle, we can call molecule. Right? We call metal molecule. If it's a lot of particles, we can macromolecule. So basically, it's an analog between actual molecules with these artificial metals. Right? And you can imagine this will introduce many different properties which different from existing materials. Right? So open up a lot of opportunity to create artificial matter with property even not existing in the nature. So just one example, simple application. If we can do this cluster in the solution, let's say we introduce the gap between particles which support a very strong localized electromagnetic field. Right? So we can use that to do surface enhanced Raman spectroscopy for the molecules. And simultaneously, we can collect these molecules into this cluster, and we can see very strongly enhanced signal from the molecules in their native environment. Usually, people have to immobilize molecule on the substrate, right? But here we can do in their native environment, which make us a lot of convenience for biological studies. Another example, how powerful that this assembly can create a new property simply using 3 particles, right? It's nothing special, just silicon particle, a golden nanoparticle, right? And so usually they just scatter certain wavelengths. But when we assemble them in a very specific configuration, here the configuration is we call chiral structure, right? 1, 2, 3 different sides. We can arrange it this way or that way. It's left-handed or right-handedness, right? So what's happening when you have this kind of a chiral structure? You introduce a chiral optic signal. Right? So if you measure CD, we call it a circular dichroism, which shows you the difference between this type of structure absorb or scatter left-handed light or right-handed light. Right? If you see the value is not 0, which means they have difference. Right? They have a chirality. So you can see this can enable us to create this chirality, which is very difficult usually. But a lot of time we know the biomolecule is chiral, right? And drug medicine, the molecule is chiral too. Right? But a lot of time to measure chirality, you have a lot of samples to have some very strong signal to achieve certain signals. But a lot of time you don't have so many samples, right? So if we have this type of optical structure, we are able to enhance those molecule signal, enable us to buy very sensitive detection of those signals. But I will talk more about later on. Okay, so now when we assemble those colloidal structures, like artificial matter, they're still suspended. But for a lot of us may be interested in devices, solid state device, right? So now we have to fix those particles into substrate, right? So what do we do? So one idea what our lab pushing is to so using, instead of solvent like water, here we can do the same manipulation in the hydrogel, right? So the one type of hydrogel is a photocurable, which means under light irradiation, it can become liquid from solid. So now you imagine when you do assembly in this type of environment, after you assembly, you can shine a UV light and you can solidify it, right? You become a piece of a solid device. So we can do many different type of structures and solidify it. Right? So that's one approach we can do. But we can also do the second approach. And instead of introduce different hydrogel, here we can check a little bit of the laser beam. We are working for assembly. We can achieve printing. Right? So what's happening here, if you kind of increase the power a little bit, so here is a trapping region, right? Here's the optical power we use. When you increase the power, right, so you will reach certain region here, it basically is printing. So now, instead of holding the particle, you push particle towards the substrate. So the particle will be immobilized on the substrate. Right? So that's exactly what we do. So we can print the particle into array on the substrate, and when we rinse it, it can still stay there, which means the bond is very strong between the substrate. And the bond is still take advantage of the depression attractive force, right? So we didn't add anything extra using the original system to achieve this printing, simply improve the optical power. Interestingly, this type of printing is not permanent, right? Sometimes when you're printing wrong configurations, we can correct it, right? Instead of throw away the sample. So that's exactly what Ling has been demonstrated, that in his experiments, he arranged this particle into, here's a lot of particles, printed them into this pattern. It's a side effect if you look at the control, right? But he can purposely re-irradiate the laser beam into this particle. So this particle can be released. What's happening? When you re-irradiate the particle, and you can squeeze the missile underneath these particles. So the repelling force will release the particle from the substrate. And then he can recapture another particle and put the new particle in the new location, and you see now you turn from sad phase into happy phase. Right? So this is a very versatile capability for us to do manufacturing at such a small scale. And so far, we have been talking about, usually it's a colloidal particles, and people usually say it's a zero-dimensional nanostructure, right? But a lot of intrinsic properties also come from one-dimensional nanostructure or two-dimensional. So our technique is general, and we apply to also one-dimensional here. And as Xiaola recorded this video, show you that, and we are able to manipulate those silver nanowires, and not only their orientation, not only trapping the position, but the orientation. We can print the one down on the substrate, then bring another on top. We can do orientation control, and then we put them together. So this basically gives us the one approach to build circuits using one-dimensional structure as elements. Now, another example is two-dimensional. So from 0 to 1 to 2 dimensions, here is what Zheng has been working on. So using what we know, two-dimensional materials become very popular, from graphene to a lot of atomically thin 2D materials. But also those nanoscale thin film membrane also show very interesting property, right? One of it is still with metals, right? It's a golden membrane. If we can create those nano holes, right? So you can imagine here, instead of individual atoms, individual vacancy of atom, now we have nanoscale holes array in this membrane, right? And we can, for the two-dimensional membrane, usually we just can do stacking, stacking layer by layer, which is a very popular concept for 2D materials, the heterogeneous integration. Here we can not only stack them together, but also we can control orientation, because the lattice constant, the lattice orientation will affect the coupling between different layers. So you can introduce more different optical property. Right. One of the property is that when Zheng bring them together, and he can purposely locate the orientation between two layers, right? He can locate top layer on the right-handed or the left-handed. When located different way, then he measures the optical property. What's happening is that, and this type of structure, right, show very interesting chiral optical response. Right? And the chiral signature depends on how much you rotate. How much you rotate. So you can basically give you a very good approach to control the chirality of the materials. And we have developed a very good theory to understand what's happening, the mechanism. So enable us to do very rational design, right, to achieve specific properties we want for certain applications. And one application, and he demonstrated, is that basically because of just I mentioned, chiral is so important for a lot of pharmaceutical application, because a lot of drug molecule is chiral. Right? And a lot of times, unfortunately, the one type of handedness is drug, the other handedness becomes toxic. Right? So that's become very trouble for a lot of pharmaceutical industry. A lot of accidents are happening because of this impurity of the handedness. Right? So how to detect, analyze the molecule you synthesize, right? Whether it's left-handed or right-handed, and even purify it becomes very important for the high-efficient drug. Right? So we show that usually to measure the chirality of a molecule is very challenging. People using bulk systems need a lot of samples, which not always have for some rare drugs. Right? But here we show that using this type of chiral metamaterials, using two-layer two monolayer nanohole array of the gold thin film, we're able to create a metamaterials, enable us to do surface-enhanced chiral analysis. Right? So you can see we're able to detect the chirality of the two drug molecules with high down to picomolar concentrations. Right? So this drug molecule has been really a disaster before, because this is a drug for sleeping for sleeping pills, but once you have another handedness, you create a lot of birth defects. Right? So it's very important to detect the purity of these molecules. Also, instead of putting these two layers, right, close contacted, we can also introduce a functional materials between these two layers. So now you can see you have this top gold thin film, then you have this bottom gold thin film with nano hole array. Right? Between them, you can sandwich a spacer layer. Right? By doing this, optically become more interesting, because if you may not be familiar, but for surface plasma field, right, people notice for thin film they can support SPP, we call surface plasma polariton. Right? But if you have two layer, have a gap, you support another mode we call GSP. It's called what is called slow? Gap surface polariton. Right? So now you have these two type of mode, and these two type of mode you have very different property. Right? Interestingly, these two type of mode can coupling. Once they're coupling, they are introduced a much stronger chirality. Interestingly, right? So you can see now we are basically can have very strong CD signal simply by control the thickness, right? To control the coupling between these two modes. And what we call is called a final enhanced. Right? There's if we are interested, this paper give you a lot of physics, a lot of mathematics, if you like. Right? But here I don't go too much in detail. So what we can do for this? Right? This gives you another opportunity to sensing or active control of the chiral signal. Right? If, for example, this media, right, this intermediate layer is a functional materials. Here is a silk. Silk is very interestingly is because the silk can change its shape. Right? The silk thin film can change its shape. Depends on what kind of solvent they are exposed. If the solvent is a low polarity, it will shrink. If it's a high polarity, it will expand. So now you can basically introduce silk to control the distance between these two membranes, to control the coupling, right? So to control the final resonance and to control the CD signal, right? So you can see by simply change different solvent, right, with different polarity, water, methanol, IPA, this chlorobenzene, you can see we can see different signal, right? They change dramatically, right? This gives us opportunity for sensing. Because a lot of time you have water, for example, in IPA, a very, very low concentration of IPA in water, it's harder to detect, because optically not much change. Right? If you measure the refining index, it is still 1.33. Right? So a lot of optical sensor based on refining index doesn't work here. But if based on our new mechanism, because of the polarity change, will introduce silk expansion or shrink, we're able to through this different transduction mechanism to do high sensitive sensing of those solvent contamination. Now you can see even 1%, 2%, 3%, you can see a larger change. Right? So you will easily detect those contamination. This type of detection is very important for oil industry, right? But in particular for gasoline, you notice how pure we need for the engine to work properly. So using this technique, we're able to detect those low concentration and solvent contaminations. Now imagine you keep enhance the power of the laser beam, what will happen? Now we say we heat the substrate become heat. You have temperature gradient to do trapping. So what if you keep increase the power? This is a question.
Vaporize your substrate.
Vaporize substrate.
Yeah.
That's what happened. Yeah. What up a little bit in the middle stage? Right, bubble created. Why? Because now the water become vaporized. Right. So this introduced another technique. We take advantage of the bubble generation. Right. We call a bubble pen lithography, which Lincoln discovered in 2016. So in this case, you see, once you have this, the laser power, I say it's a high power. It's exactly not that high. Compared with optic teaser, it's still low power. Right. The reason we can using low power generate a bubble here is because secret with that thin layer. Where this thin layer is, golden nanoparticles, small golden nanoparticle, we know support the surface plasma. Right? In the first few slides I mentioned, once you have surface plasma generated, you can concentrate the light in such a small scale, you have very high conversion efficiency of light to thermal energy. Right? So you can easily heat up the water. So now you have this bubble generated. Right? Also you have this high temperature gradient. So what's happened? Just like you're boiling water, right? Now you have this convection. You keep bringing the water or this particle towards this laser beam position. So if there's no bubble, you can imagine the particle will keep dancing around, never stop, right? Unless you reduce the temperature. But what's happened if you have the bubble here? So when the particle touches the bubble have very strong surface tension, which you can capture the particles. So now you have this bubble holding the particle, and once you move away the laser beam, the temperature goes down, the bubble collapses, right? So just like you hammer, and you can push the particle towards the substrate and put them on the specific location. So that's exactly what we do with the bubble pen lithography. We'll create a bubble at one location, grab the particle, put them down, another location, another particle, put them down, and we can using the DMD system digitally control the laser beam to spell different patterns. So now basically we have created a printing systems, right? Instead of using ink, we're using colloidal particles as a pixel to create the pattern. And of course, we can control the bubble size, right? When the bubble is larger, using high power, you can grab a lot of a particle instead of a single one, right? So you can control each pixel, basically can control the pixel geometry, right? Simply control the power intensity. So this video shows you how quickly this processing can happen, right? Usually convection at the nanoscale is very slow, but we introduce bubble, enable us to make this process really fast.
This is basically that.
Exactly.
What's old is new again. In Texas now, where scientists have mastered another difficult maneuver. No Knight Rider, but it's pretty good. How do you manipulate microscopic nanoparticles? Well, simply, you just trap them in a micro bubble and then use a laser to move them around. That's what engineers at the University of Texas are doing. They call their technique bubble pen lithography. Moving the nanoparticles around with bubbles avoids handling them directly, and that lowers the risk of damaging them. And these are great tools when scientists want to start building their tiny futuristic machines.
We're always getting.
So you can see that when you have the bubble on the right side, the particle comes really faster, right? It's not just conventional convection flow. You have to also another flow called Marangner. Yes, you hear? Okay, good. So make this really faster, right? Because the bubble have the surface tension, right? Introduce another flow. So make this really, everything works so nicely, right? So it's also fascinating. Another member of Ross, he think he can basically this technique can compete with printing, inkjet printing. So he pushed this system into printing different type of particles. Now here is the example shows the Conan dots. Right? Conan dots, you can see here basically using Conan dots to create different patterns. What he do is basically Google the website and find the interesting figure he's interested and put it into computer, and computer will scan the laser beam and create those nice images on the substrate. Right? It's a nanoscale features using Conan dot, which are a couple of nanometer scale. We can also do multiple different type of Conan dot in the same system, right? You have orange, this different color, and different color Pennsylvania, where I came from. UCLA, I go my postdoc, and here now in Austin. So that's exactly he can do in the series to do a different type of particle printing. And we talk about a lot of in nascent about the row-to-row, about the flexible substrate, right? And the same thing we can do using the system. We are able to printing the structures on the flexible substrate. Here is a polymer substrate, and we can create exactly precise features and as on the solid state substrate in rigid substrate. And more interestingly, we not only put down the structure, right? We not only put down the particles, we also maintain their original property, right? If you damage it, that's become a trash, right? No use. So we have to make sure the property is still retained, but more interestingly, we are not only can retain original property, we are able to precisely tuning the property through the printing process, because the printing rely on the temperature heating, right? So through the intrinsic heating effect, by control the scanning speed, we're able to tune the fluorescence of the Conan dot eventually when they print on the substrate. So you can see we're able to patterning and simultaneously control the property. And also, it's become very interesting areas to integrate the 2D materials, graphene, another 2D materials within quantum dot, 0D structure to form hybrid systems, right? To introduce more interesting phenomena. So our capability to printing these particles on 2D materials give us a very good platform for fundamental understanding, right? So if we are interested in the Minson, which give, using this platform, the 2D materials, particles, study a lot of interesting phenomena between the 2D materials, 0D particle, the energy electron transfer, right? So a lot of interesting phenomena be discovered. So we believe if we can control those particles in a much better, precise fashion as what we do in the printing, we're able to control of the properties in a more precise way. And not only we can print the particle which already synthesized, right? And we can even introduce another step which chemists have to do it to synthesis, right? We know we can just start with the precursor, right? Without synthesize the particle first, we can start with the precursor. What's happening here? Basically the same thing, because our bubble printing doesn't depend on what type of particles, right? Regardless particle, regardless molecule or ion, everything can be concentrated through this convection at the edge of the bubble. So now you can imagine when you have these ions be concentrated at this edge, you have also heated the substrate, right? Chemical reaction can happen, right? And so interestingly, this can happen in a very different way. You can generate new materials which conventionally cannot be synthesized. Also, you can save a lot of time because now you have this high concentration, not rely on diffusion anymore, right? Diffusion can be very slow. So we are basically is a process that be intensified, right, for the chemical synthesis. So example shown here is that basically we are able to do synthesis and at the same time do patterning of these silver structures, right? Start from silver precursors. So what we can do with this silver structure? One example is these silver rings. Can support a very good surface plasma resonance at a different wavelengths. So when we can push them into middle IR or near IR region, so we can do surface enhanced Raman spectroscopy using this real-time road structure and in the very, very small microfluidic channel. That's an advantage for using light, right? If you mechanically or other chemical way, there's no way you can precisely put a specific ring at a specific location in this small channel. But using light, it's a remote control, and we can do real-time synthesis. We can achieve this. And we can achieve this structure in the lab-on-chip devices, and we can do a very high-sensitive spectral analysis. And also, we can do something which, as I mentioned, not easily to be synthesized conventionally. Right? In particular, the alloys which using composed of elements not mix each other well. Right? So we call immiscible. Right? A lot of time, this alloy is not immiscible, but interestingly, when you can find somewhere to mix it, you can form very new property, like catalytically, for example. Now here, using this technique, because of our super saturation capability, right, at this nanoscale at the interface, right, which if you know more theory about this, and the paper will come out soon, I think Pavana have very good theoretical understanding, and we have more following work, also homework, have been work on push this better understanding so we can have better control in terms of throughput and also the elements of the compositions. So you can see we can achieve really good alloys, which show in this TEM image. You can show those also show that not only we have IH, we have of gold. They form very good alloy. Right? So as a catalytic demonstration using this type of alloy, you can show that. We can show that, and this give you a much high catalytic capability on here, conversion efficiency for this type of chemical reactions. So basically, these are very good platform to us create new materials. Right? Not only synthesize them, but also pattern them in the structures we want on the substrate. So far, I have been talking about everything is like a bottom up. We're using particle, nanowire, two-dimensional membrane as a building block, right? To stack them together, assemble them together into microscale, macroscale materials. But there's another approach we can use called the top-down, more like lithography. And with the same system, we can apply because because of our capability to control the laser beam using DMD system, we can digitally control the laser position, and as a one demonstration, we are able to achieve all the nanolithography using optothermal plasmonic effect, which Zheng and Lin has been working also with collaborate with Wei and from Deji's group, and so we can show that by simply scanning the laser beam, right? And we know once we have these 2D materials, graphene or other 2D materials, if we can hold a single gold particle, we can hit it. So this basically is a nanoscale heat source. So you can imagine when you scan through this subject, the chemical reaction, the thermal heating treatment can happen, make this chemical bonding broke. So basically now you're cut through this membrane into different patterns. Or you can have a lot of small particles as a thermal source on substrate. Put the graphene down, you can scan your laser beam. So whenever you have laser beam, you heat up, right? You can do the similar patterning. So this is exactly what has been shown that through the same thing as bubble pen lithography or other technique, we're able to using the image from Google website, right? And we as input. So to transfer those images into structure of the graphene or 2D materials. Right. So this gives you a very versatile way to patterning the 2D materials into nanostructure for different device applications. And now we push into how can we integrate the system, even work on the flexible substrate. That's what Jimmy has been now looking to another new student to on flexible substrate for more interesting patterns, so we can do like tattoos, flexible electronics, photonics. So these days, everyone have smartphones, iPhones, right? So to make our manufacturing tools or fabrication tools more accessible to different users, we have developed apps which enable us to using iPhones to control the system. So you can even kids can play with this. You can load the pattern on the iPhone and then send the image to the computer, and the computer will write as whatever you draw, right? So your tone in the macroscopic using hand, right? And basically you now can create a feature at the nanoscale, right? So this is what we call haptic, right? These days the artificial reality has become so popular, or reality argument, right? Maybe one day we can just put on the goggle, even using our motion to control this manufacturing, or even we can go further, can sense the manufacturing process. During this writing, can we sense any mechanical motion to give you a real experience, right? As science and entertainment come together. So, as a summary, I think we believe that the digital manufacturing, because of the advantage of the DMD system, and give us very powerful tools to create the nanostructures with very complex architecture and novel functions, right? Because of the paradigm shifting from conventional optical teaser, which is high power, very complex system, now we're using new mechanism to reduce the power. Using very simple system, we believe that this enables us to further scale up the throughput of this type of manufacturing. Hopefully one day we're enabled to have this portable system for customized use for different type of nanostructure and push those materials into different applications. So thank you for the opportunity. I'm happy to answer questions. Questions?
So is the size of the nanoparticle you can track dependent on the spot size of the laser? Or do you get away from that with this bubble where the interface is much smaller?
Yeah, small. That's, we basically using this kind of Bragg diffraction limit. Right? Using bubble, generate a bubble, you can grab one particle. Right? But when you put down, how precisely you can put down, it depends on kind of random again. Right? But now we are engineering another subject, which using antenna. The antenna can confine the thermal heat in a much small scale, which I not show here. That another ACS nanoplate by our another student, Yolan, and so the ACS paper he shows that through the antenna engineering, we're able to create a very small thermal heating source. So you can imagine beyond the diffraction limit of the light.
All the videos that were present, those were shown in real time?
Some is real time, some is not. Yeah, some video actually takes hours, and Lincoln can tell you his experience. Even stay overnight, I guess, to get the video. But here, when I present, a few minutes. So yeah, I feel bad, but
I just wanted to have a sense of range of time scales.
yeah, sometimes it's that assembly that's 2 to 3 times faster.
Yeah. So for the 2D sheets that are rotated, can you control the relative angle by like heating a large area and then moving the plot size? Is that how the rotation is done?
Yeah, so I think now we are very fortunate because we don't have very sharp eyes. So basically now he visually sees the orientation. But for manufacturing, for real time, for the robots, now we have the current proposal for the equipment. So we get automation and real time monitoring of the angles. Hopefully we can got it this time, so we have the system. Please.
Can you do the bubble lithography with nanowires?
Yeah, actually that's now what we are pushing, and I see he's smiling because he's addressing his problem. Not only put down but control the orientation. You talk about bubble printing or other technique? Yeah, floral, right? Dynamic pattern change, you mean? Oh. Yeah. So bubble printing. You mean for bubble printing technique? Yeah, for tweezer, we are really sure we can do floral. And for the bubble printing, we can have many laser be portable to do floral fabrication.
Can you put in place different types of nanoparticles with the same laser or at the same time, same liquid?
So in the same liquid, you have different particle. Is that your question? And so can we grab a different particle? Yeah, because the trapping is not dependent on what kind of particle. As long as we can see that, we get through imaging, we're able to hold a specific particle. Is that the question?
Not on a bigger scale. It has to be find the particle and then trap it.
The advantage for us, especially, we have a much longer working range compared with optical tweezer because we through this thermal delivery. So we can work even as long as you have this optical view, you can see those particles. Even beyond the view, we can see particles coming.
What's the resolution of the features? How small are the nanoparticles?
You talk about which technique? Is it trapping? Bubble pen. So we can even work with molecules. So there's no limit in terms of size. But then when you go to too small, we started seeing how precise you can put. Right? So that's limited by the bubble, by those hydrodynamics processing during the bubble collapse.
You mentioned there's so much material here, pardon the pun, in terms of just the fundamentals of nanomaterials. But one of the applications that attracted my attention was your talk about the chirality of medicine.
Mm-hmm.
And so I was curious what you see as the limitation and what limits the potential of the application of these techniques versus the current capability to distinguish between medicines of two chiralities.
Mhm.
So focusing on that specific example, what's the state of the art of current manufacturing methods for thalidomide versus what you see as currently limiting application of these new techniques?
Yeah, so actually, this we started talking to the company which work on this type of medicine, and so one type of future work we are pushing through large scale manufacturing, row to row, which have give us opportunity not only high throughput but also every time it's reproducible. This type of alignment and this type of size control, which will become critical for large scale applications.
Well, I should probably ask you offline. I was curious what the current state of the art is in terms of deviation from their ability to provide your, a particular chirality for your drug, but that's a rather involved question.
Yeah, so in terms of this kind of detection, yes, here we still kind of at a relatively early stage, because when you have several type of chirality, when they're mixed, how can we differentiate them? How much percentage? That's become a little bit of a challenge because we have to make sure we calibrate the system well. But I think we are introduce another machine learning. We try to introduce a new type of concept that big data. Hopefully, we can solve this type of challenging.
Well, if there are no further questions, we can end here. We have the room for at least another half hour, so you can continue the discussion offline. But let's thank our speaker again.